Right, we are discussing dust solutions of the Friedmann equations. So in this case, the two equations we want to solve is order, please. The equations we want to solve are this equation 3 over a squared a prime squared minus lambda c squared. And we did it with a vacuum case last week. And now we have a mass density mu here, which of course is assumed to be positive. Yeah, we consider the case that in this chapter we consider the case that mu is strictly positive. The case mu equals 0 has already been covered, and the case mu smaller than 0 is usually considered unphysical, so we won't do this. And the second equation was minus k minus a prime squared over c squared minus 2a over c squared a double prime plus lambda a squared is 0. We don't have a pressure. We consider a dust. Okay, and before I solve this equation in general, actually I will, what I'm planning to do is to discuss the solutions completely for lambda equals 0, and then to make a few remarks how these solutions are modified by lambda. So I will not consider again all the possible cases in full detail as I did for the vacuum case, but I will do the case with lambda equals 0 completely. But before I talk about the general method of how to solve this system of equations, so it's now two equations for two unknowns. Yeah? The two unknowns are the a, which is a function of t, and the mu, which is a function of t. So these are the two unknown functions. And I will show that one can reduce this to one equation for a and then determine the mu afterwards. But this method doesn't work for the static solutions. For these reasons I have to do the static solutions first to have them out of the way. The static solutions, so these are the solutions where a is a constant. That's what I mean by static. So a of t is a constant, let's call it a naught. So let's see what we get for this case. Then the first equation, this term is 0. The first equation requires that this is a constant now, minus lambda c squared is kappa c to the 4. And this, of course, must also be a constant. Yeah, because if the left-hand side is constant, then the right-hand side must also be constant. So let me write mu naught here. Minus k, this is 0, this is 0, and I have this only. Is 0. So what does this tell us? This tells us that I can eliminate lambda from these two equations. So lambda, according to the second equation, lambda is k over a naught squared. And according to the first equation, lambda is 1 over c squared times this. This is 3k over I naught squared minus this term, c to the 4 mu naught over c squared. Okay? So these two things must be equal. So from this equality I get, 3 minus 1 is 2. I have 2k over a naught squared, and this comes to the other side. Kappa c to the 4 mu naught. I can cancel this, of course. Okay, what does this tell us? We assume that the density is positive, so it only works with a positive k, with k equal plus 1. Yeah? It doesn't work with k equals 0 and k equal minus 1. And if k is plus 1, then this equation tells us that lambda is k is plus 1 over a naught squared. So we see it only works with a positive k and a positive lambda. Yeah? It does not work with a negative lambda, it does not work with lambda equals 0. And this was the observation Einstein made in 1917. When he began, he considered what we now call a Robertson-Walker universe. The Robertson-Walker, the paper by Robertson and Walker were much later, but it was exactly this kind of symmetry he considered. And he considered a dust, and he wanted to find a static solution without a cosmological constant, which didn't exist at this time. And he saw it didn't work. Yeah? So he tried to solve these equations with lambda equals 0, and it didn't work. And then he introduced the lambda, and then he saw, aha, then it works. And it works with a positive lambda. So of course the mass density is also positive. So we have now k equal to 1. So I can solve this for mu naught. The mass density is 2 over a naught squared. Kappa c squared. Yeah. So if I fine tune the lambda and the density in this way, then I get a static universe. And how does the universe look like? So the metric is minus c squared dt squared. Our scale factor is a constant now, a naught squared. And the spatial part, we have k equal plus 1, so I have here the sine squared, the omega squared. And actually, we have considered this metric already on one of the worksheets. I just gave it there without deriving it in any way from a field equation or in any different way. I just gave it as an example for a Robertson-Walker spacetime, where we studied the time a particle needs to travel once around the universe. Yeah, the universe is a sphere. The spatial topology is that of a sphere because of k equal plus 1. And we calculated the time a particle needed to travel around this universe, and this is called Einstein's static universe. And how does it look like? Well, it has spatial sections which are spheres, and it is static. So all the spheres have the same size. Yeah? So it looks like a cylinder in this representation where these surfaces t equal constant. They are just circles in this picture, but actually they are 3 spheres, yeah, because 2 dimensions are missing. So it looks like a cylinder, and therefore it's sometimes called Einstein's cylinder world. Yeah? You also find it under this name in the literature. And that's what Einstein suggested as a viable model of our universe in 1917. It was the first cosmological model which was ever suggested as a result of Einstein's field equation. And immediately after that, De Sitter wrote his paper, where he introduced what we now call the De Sitter universe. So for the sake of comparison, let's remind ourselves what the De Sitter universe was. One of the representation, actually the most natural representation, was that as a world with sections which are the sections t equal constants are again 3 spheres, but in this case the radius is not constant. Here the world is contracting and then re-expanding. And so here we have a density and we have a positive cosmological constant. If you recall that this was a vacuum solution, so mu equals 0, and this also had lambda equals 0. And these 2 world models, they were suggested in 1917, this by Einstein, this by De Sitter, and they were competing for a couple of years. Actually, for at least for 5 years, as far as I know, these were the only cosmological models which were discussed in the literature. Then came the Friedman paper, and this more general class was introduced. And actually the 2 gentlemen among themselves had a very vivid discussion. So they exchanged letters for over a long period. They are preserved, so you can read about what Einstein said about the Sitter universe. In the beginning he said, this is complete nonsense, let's forget about this. And the Sitter tried to convince him that actually the universe is a very reasonable thing, and Einstein made a few steps back. And so they discussed this for quite a while. To jump ahead, this controversy was then solved in a rather democratic way. When the expansion of the universe was discovered, then both gentlemen thought, let's forget about the cosmological constant, we don't need it. And they then wrote a joint paper about another universe, which was called Einstein De Sitter universe, which they both agreed upon that this would be a reasonable model. We will talk about the Einstein De Sitter universe in a few minutes. But so this was a historical development. And what we see here is that the Einstein static universe is the only dust solution for the Friedman equations. And we need a cosmological constant for this. So actually here we can read again the fact that a positive lambda has a repellent effect, right? So here I have no matter and only the cosmological constant. What the cosmological constant does is it pushes the whole thing apart. Yeah? So the universe has an initial condition, it comes in contracting, but then the cosmological constant pushes it apart. you have both things. The cosmological constant, which would like to make it expand, and the mass, which of course is self-gravitating, so it wants to attract everything. And the two things can be balanced if you fine-tune the parameters in this way. So again, you can read from these facts that positive cosmological constant has a repellent effect. Okay, so now the Einstein static universe is out of the way. From now on, we consider only non-static solutions to these equations, and for these cases, we can reduce this to one equation. And to do this, as an intermediary step, we have to derive from these two equations a conservation law. So my claim is that F1 and F2 together, F1 and F2, imply that this quantity mu, which is a function of t, and a, which is a function of t cubed, that this is a constant. So that this is a constant. Let me write the arguments. So in general, mu is a function of t, a is a function of t, but for every solution of F1 and F2, actually this combination does not depend on time. Do you have an interpretation for this conservation law, or does this come as a surprise to you? We have a dust. So the only form of energy is the rest mass of the dust particles. And mu is the rest mass density.
Is this density times volume?
It's density times volume, yeah. So it's a conservation law for the mass, yeah. So actually this is not a surprise that this holds. Yeah, if it is a spherical topology, then the A is just the radius of this S3, and mu times A cubed with a factor is just the volume of the 3 sphere. I think the factor is, what is it? In 2 dimension it is, it's 2 pi, right? 2 pi r squared. In 3 dimensions it is, wait a minute, 2 pi squared? I think anyway, so this is the appropriate factor of which involves pi in front of this. This is just the volume of the 3 sphere. Okay, let's prove this. So actually, if you recall that this is just what is left from Einstein's field equation. Yeah, all the other equations are triviality. That's the only non-trivial components of the field equation. And you know that from the field equations you get the conservation of energy. Yeah, the conservation of energy is this covariant divergence condition on the energy momentum tensor as a consequence of the field equation. Then this kind of conservation law must result from the field equation, and it does. So how do we prove this? Let's begin with F1. Oops, let's begin with F1. And let's take the derivative of, I'm interested in what happens to mu times A cubed. So let's begin with this expression. So let's write kappa c to the 4 mu times A cubed. This is what? So I have to multiply the left-hand side with A cubed. Then I get 3c squared k times 1a. Yeah, A cubed over 1 squared is 1a. Plus 3 a prime squared a minus lambda c squared A cubed. And from this, we get by differentiation, these of course are constants, so I get the derivative of this here is what? So I calculate the derivative of the right-hand side, then I get 3c squared k a prime plus 3 a prime cubed plus 6 a prime a double prime a minus 3 lambda c squared a squared. Okay? And I have an expression for a double prime. I forgot an a prime here, right? Yes, chain rule, right? I differentiate with respect to t. So, well, first of all, I see that I can take an a prime out of the bracket. Then I get 3c squared k plus 3 a prime squared. And here for a double prime times a, I have an expression from F2. So I'm using now F2. So what is a times a double prime? A times a double prime is c squared half times something. And this something is, so I take this to the other side, minus k minus this plus this. Minus k minus a prime squared over c squared plus lambda a squared. And then I have the last term, this here. Minus 3 lambda c squared a prime, and I have taken the a prime out of the bracket. Okay? I forgot it here. Yes, I have taken the a prime out of the bracket, so it's gone here.
Can't you just multiply the second equation with 3c squared a prime, and then this is exactly your right-hand side, and you see that it must be 0.
Oh, you see it in a quicker way, yes, but it should come out also this way. Let's see. Well, what I've done is exactly the same calculation written in a somewhat more complicated way, but I think you're right. You can do it in a more elegant way, like that. So what is this? 3c squared k, 6 over 2 is 3 minus 3c squared k. 3a prime squared minus 3a prime squared minus 3 lambda c squared a squared plus 3 c squared lambda. So the whole thing is 0. So the conservation law holds. Okay? So, and now comes a somewhat subtle point. So the idea is now we have this conservation law. This conservation law determines mu if I know A. So is it sufficient to solve an equation for A and then determine the mu afterwards? Or do I really need both equations again? So the claim is, the second claim, so this proof is now finished. So let me write this down. Suffices, let me give a name to the integration constant. Let me see how it comes out. So my claim is sufficient to solve f1 in the form, so what was f1? So let me write, let me multiply everything with a cubed, so let me write it in this way. 3c squared k a plus 3a prime squared a minus lambda c squared a cubed. Or I think I take I divide by c squared. That's nicer. I divide by c squared, and I have to divide this also by c squared. So I get kappa c squared mu a to the a cubed. And this is a constant. What's the dimension of this constant? Well, k is dimensionless, a is a length. Yeah? So this constant must have the dimension of a length. So let's call this a naught. And this is a constant. Yeah? So let's solve this equation with a constant a naught, which you choose as you like, and then determine mu from this equation. So mu of t would then be, if I solve this for mu, I have a naught divided by kappa c squared a of t cubed. Yeah, so if I have determined a solution A of the first equation with a constant a naught, and then determine the mu from this equation, then I claim that then f2 is automatically satisfied. And there is a subtlety with this, and that's the reason why I want to really demonstrate this again. Then f2 is automatically satisfied. And I leave a gap here. Actually, I have to write a condition there a little later, and we have to see what this condition is. So what I do now is I try to verify that f2 is satisfied if I have solved this equation and my mu determined by this. So if I take the derivative of this expression, that I get f2. And I do this on the board because there's a subtlety about this. So it's exactly the same calculation which we have done before, but now the other way around. Yeah? In the proof of this claim up there, we have assumed that f1 and f2 hold, and then we have derived the conservation law. Now we assume that f1 holds with the conservation law, and we want to demonstrate that then f2 holds. So we do the same calculation backwards. Does it work backwards? And it works almost everywhere. So let me see. Yeah?
Question about the zeta universe. For the first branch, the universe collapse, but the mass density is zero. How it can collapse?
Okay, so the question was about the de Sitter universe. That in the beginning, in the first half of the time, the universe is collapsing, but the mass is zero. How can it collapse? Well, of course, the answer is it depends on the initial condition. Yeah, if you start with pushing all the particles inward, then they will continue moving in this way for a while, and then the repellent effect of the cosmological constant takes over. So everything depends on the initial condition. Of course, you can also construct solutions with mu bigger than 0 and lambda bigger than 0, which are non-static. Yeah, it depends on how you balance the two things. Yeah, if the mu is bigger than the effect of the lambda, then the whole thing would contract, and if the mu is smaller, then it's the other way around. So it depends always on the initial condition. That's something you should keep in mind. It's a differential equation, right? So it depends on the initial conditions.
But isn't there a subtlety as well? You said you start pushing all the particles in.
I shouldn't have said particles. I shouldn't have said particles, no.
What do you push inwards?
The universe, yeah. The universe.
So space.
It's space, yes. So the space there's an initial condition for our universe, which means that in the beginning, all the I can speak about standard observers, yeah? They are not necessarily massive particles, but I can speak of standard observers. The initial condition is that the standard observers move towards each other. And then after a while, the effect of the cosmological constant will make them move apart. Okay, I wanted to prove this statement. So I should give this equation a name. Oops. Let's call this. I think I had in the script I had sometimes an f prime. So let's denote this f double prime here with a naught. So f double prime. F double prime. So if we now calculate backwards, if we differentiate this, do we really get f2? So then we had, well, it's exactly this expression here, but with a prime. Yeah, we get this now. We get, let's call this star. So from f1 double prime, sorry. We get star. And now the subtlety is that from this you get f2. This is f2 with a 0, only if you are allowed to divide by a prime. And actually this is something I overlooked in the beginning when I prepared for this lecture. I just stroked this away and didn't think about it. Yeah? And then I had this solution and I thought, okay, I've proven that f1 always implies, that this version of f1 with a conservation law always implies f2, so I don't have to care about f2 anymore. And then I saw that this equation with a naught on the right hand side has a solution with lambda equals 0, a static solution with lambda equals 0. But we know, everyone knows, that solutions of this kind don't exist. I wondered for a while, where have I made a mistake? Yeah? Why do I get this wrong result from calculating correctly? And the reason was that I had divided by a prime. And of course, the static solutions have a prime equals 0, and then it's not allowed to divide by a prime. Yeah? So this results that you can reduce the two Friedmann equations to this one condition in the case of a dust. Doesn't work for the static solutions. It works for everything else, but not for the static solutions. We get f2, and this we get this, and this implies f2 if a prime is different from 0, because we have to divide by a prime. And so I have to continue this sentence here. Then f2 is automatically satisfied if a2 is different from 0. But if a prime is different from 0. But it does not work for a prime equal to 0. Well, the relevant thing is that we have to exclude the case that a prime is really 0 on a whole interval. If it is just 0 at one point, then we can still consider these equations on open sets, and by continuous extension we can still apply the argument to the whole solution. So this matter of not being allowed to divide by a prime becomes relevant only if a prime is really 0 on a whole interval. So isolated zeros don't matter. So for this case it works. Okay, what I wanted to say is that from now on, when we discuss dust solutions, we only work with f1 prime, f1 double prime, yeah. And let's look at this equation. And yeah, as I said, I will solve this in general for lambda equals 0. And the case with lambda, then for this case I will make a couple of remarks. So then we have the equation we have to solve is this here. So let me write it down again, and let me solve it for a prime squared. Then I have a prime squared minus what? So the first term is I divide by 3 over c squared. So the first term gets a c squared k, right? So it's c squared k, and then I have divided by, is there something wrong? No, it's correct. It's correct. So this is this here, and on the right-hand side I have, actually I want to order the terms in a different way. Sorry. So let me write the right-hand side. The right-hand side has an a naught, and I divide by 3a over c squared. 3a over c squared. And on the other side I have only the first term, but it comes to the right-hand side, so it is minus k times c squared, right? Minus k times c squared. So that's the equation we have to solve. And if you look at this, I will solve it in a minute. But before you start any calculation, maybe it's a good idea just to look at this equation. Doesn't look this familiar? It has a structure which should look very familiar to every one of you. If you compare this with the energy conservation for a particle in classical mechanics, then you see it's very similar. There you have an equation of the form kinetic energy, I set the mass equal to 1, yeah, so let's forget about the mass. Then I have a potential, and here I have the total energy. Yeah? And that's exactly the same structure. Yeah, second derivative of an unknown variable. It's the position of the particle here, it's the radius or the scale parameter of the universe here. Then a function of this variable, and in this case it's 1 over a. And on the right hand side a constant. Yeah? So the solutions to this differential equation behave exactly, they are described by the same mathematical equation as a motion of a particle in a potential of the form 1 over x, minus 1 over x. Yeah? So if you know, I don't know if you know, but maybe you know how particles in a potential 1 over x behave. So how does this look like? So this would be v of x proportion, or let's write is a constant, some constant over, or let me just write minus 1 over x. The factor is irrelevant, and here x. So this is obviously something like that, right? That's how the potential looks like. And now we consider motions of particle with a total energy, and you see the sign of the energy corresponds to the sign of our k. So let's do it for k equal plus 1. Then it corresponds to a negative energy, so we are here. And you see, what is a particle doing? The particle comes out of the origin, moves to a maximum, and then goes back. And the same behavior we must get for the scale factor. The scale factor begins at 0, it begins with a Big Bang, it reaches a maximal extension, and then it falls back. So it's a universe which starts with a Big Bang, expands, and then ends in a big crunch. So from this analogy, we know, before doing any calculation, that the solution with k equal plus 1 must have this behavior. There's a question?
Why did you write the d square x by dt square if I compare this with classical?
Sorry, nonsense. Oops. Big mistake, excuse me. Velocity, I said kinetic energy. Of course, what I've written had nothing to do with the kinetic energy.
So I think it's F1 primed, or is it F2? Like next to lambda.
Oh, sorry, yes, again. Yeah. I mislabeling the equations. I'm always making mistakes. Okay, so if the E is positive, this corresponds to the case k equal minus 1. I have an energy here. What does the particle doing? It never hits the potential, so it never reaches a turning point. So the particle would move out to infinity forever. So in our analogy, the universe starts with a Big Bang and then it expands forever. And the borderline case is this here. This corresponds to k equals 0. And in this case, the particle or the universe, which case you consider, just manages to reach infinity, but it arrives at infinity with zero velocity, because asymptotically it hits the potential, the graph of the potential. Yeah? So this is a borderline case between a closed universe and an open universe. So this follows just from this analogy before doing any calculation. But we will do the calculations now, and then we will get the precise form of the function a of t. Okay, in order to solve the differential equation, actually we will see that, or one sees, I just tell you, one sees that it is much easier to solve it if you transform to the conformal time. Yeah, prime means derivative with respect to our time parameter little t. And actually, if you try to solve this, you will get some transcendental functions as the solutions. If you transform to the conformal time, this is not the case, and that's what I do now. We transform to conformal time, which I called capital T. Just to remind you, dt was d little t over a. Yeah, this was the way in which the conformal time was defined. It's only defined up to an integration constant. And this means that if I evaluate these expressions, that's what you have in the differential equation. Yeah? Then I can do this with the chain rule. So this is dA by d capital T, dt by d little t, and this here is dt by dt is 1 over a. Is 1 over a dA by dt. So the differential equation becomes, this was the equation which I called as double prime. If I rewrite it in terms of the conformal time, I have dA by dt squared. So this is a squared times dA by d capital T squared. Okay? This is dA by d little t squared, this term here. And then I have minus a naught c squared over 3a is minus k times c squared. Oops.
No, it's the other way around, right?
I hope so, because this doesn't look good. Where did I make a mistake?
It must be capital T, the last dA dt. It's a dA d capital T.
So where is the mistake? Let me check again. This is a chain rule. I think this is correct. And the capital T by the little is also correct, right?
Yes, but the last dA dt.
That's a capital. Thank you. Yeah, obviously this is. I realize that this is wrong. So now I express this term here, and then I get this 1 over a squared, and that's much nicer. That's much nicer. So I have dA by d capital T squared is, on the other side I have c squared times what? C squared times this here, a naught over 3. This comes in the numerator, divided by 1a gives this here. And this is a minus k a squared. Is that true? Is the 3 correct? Let me see. I think the 3 was already wrong, was it? No, I think it's true, right? Puzzled. Because I'm fairly sure in my notes I have no 3. Let me check. Yeah, I have no 3. But maybe I made a mistake here. So let's check again. I see. I put the 3 into the a naught in my notes. So in my notes I divided everything by 3, and then I defined the a naught with a factor 3 included. Do you allow me to do this on the board? Because otherwise I would be completely confused if I have a different convention in my notes. So let me divide this whole expression here by 3, and let me include the factor 1 over 3 into the definition of the a naught. Yeah? So what I have called it is also affects this here, right? So the mu is then 3 times A naught. So wherever I have an A naught, I have to write 3 times A naught now. So where do I have an A naught? This is the other. Oops, no, this is irrelevant. So I have a 3 here. Okay. This has nothing to do with this. So I have a 3 here. I have a 3 here, and then it goes away. Okay. So that's the differential equation we have to solve. And we do this for the 3 cases separately, k equal -1, k equal +1, and k equal 0. So let's begin with k equal +1. For k equal +1, we have to solve the differential equation dA divided by root A naught A minus A squared is plus minus c dt. Well, and that's an integral. You can solve it with a substitution. What you do is you complete the square, and then you make a substitution that you write a cosine or sine for the thing which is under the square, and then you can solve it. But maybe I don't have to do this on the board. You can look it up in Bronstein, and I just tell you what the result is. So the result is A. It's now, oh, sorry, this is a capital T. It's a capital T, yeah? Here, capital T. So the A of capital T is, have to look up the signs. Let me just solve the integral. So if I solve this integral here, I get the inverse cosine 2A over A naught minus 1. And if I integrate this, of course, I get plus minus c times t. There could be an integration constant, but let's see if we want to have it has a Big Bang, the universe. If we want to have the Big Bang at capital T equals 0, then this must be 0 for A equal, let me see, let me write the T. Let me see what it is. Okay, then I apply a cosine on both sides. So then I have 2A over A naught. I take this to the other side, and I have plus cosine. Under the cosine, the plus minus sign goes away. Yeah? The cosine of x is the same as the cosine of minus x. So I have ct minus t initial. And is the sign correct? I think the sign is wrong. I have 1 minus. Let me see. We have a plus. What did I do here? Cosine. I have a plus here. Maybe I should we solve this on the board? Maybe I made a mistake here. Maybe it's the other way around. Let me see if this works. If it is this way, then I have cosine of this minus 1 is minus. Then it would come out correctly. So I think I made a mistake here. I think it is this here. Okay, so that's the solution for our A. It's A as a function of capital T, right? So we can, okay, let's write it in this way. 1 minus. And now we can talk about the integration constant. So this has a Big Bang, so A becomes 0. Where does it become 0? It becomes 0 where the cosine becomes 1. And one solution is T equals 0, right? So we choose Ti equals 0, then the universe begins with a Big Bang at capital T equals 0. Yeah? So choose Ti equals 0, then we get this. Okay, so this is A as a function of capital T. Actually, we want to have A. Oh, you see, this is finite, right? Maybe I should draw a little diagram. So we see that this has a Ti, which we have chosen to be equal to 0. equal to 0. And it has a finite time where the universe again recollapses. This is when the cosine becomes again equal to +1. And this happens at 2 pi, right? So TF, or let me write CT here, then I have the C already included, then this must be 2 pi. Yeah? So the universe is defined only here in this region. This is a Big Bang, and no, sorry, this is the beginning of the world in conformal time. This is the end of the world in conformal time. We don't know if this is at the moment, if this is really a Big Bang and a Big Crunch, because this is told us by the little t, not by the capital T. The capital T tells us something about horizons. So we are in a universe with, what are we doing? K equal +1. So the natural topology is that of a sphere. So the chi goes from 0 to pi. That's the North Pole, that's the South Pole. Yeah? So each of these regions here, each of these regions is a 3-sphere. This is the North Pole of the region, of the 3-sphere. This is the South Pole of the region. And we have our universe here in this rectangle. Actually, in this case, it is not a square. You see, this has length 2 pi, this has length pi. So let me indicate this more clearly in the picture. So the height of this rectangle is twice as long as a horizontal extension, and this means we do have horizons, but the whole world comes into view in a finite time, right? At this time, when I'm here, I don't see all other particles. I only see those here. I still don't see all particles, still not. But here, also the South Pole has come into view. So in the middle of the world, as far as the time axis is concerned, the whole world has come into my view. Then I see all the other particles, and from then onwards I see all the other particles. So there are particle horizons, but they vanish after half of the world is over. And what about event horizons? Well, there are event horizons, right? Here there are events which are never seen by this particle. So there are event horizons and particle horizons in this universe, where we would like to have the scale parameter as a function of little t. If you just substitute back from the little t to the capital T with this transformation law, you see that a of little t is represented by a transcendental function. Here you have an argument once under a cosine and once without the cosine, and you cannot solve this in an elementary way. But you can represent it, the graph of the function a in the TA diagram in parametric form. To that, I have little a as a function of capital T. If I also manage to get little t as a function of capital T, I have a parameter representation of a as a function of little t, and this can be done. So what is little t, or rather CT? CT was integral over a dt, right? It is this expression here just integrated, and we now know what the little a is, so I have to integrate this expression over, I forgot a c, over CT, and what do I get? Well, if I integrate the 1, I get, so I have a c a naught over 2. If I integrate the 1, I get a t, and or let me write the c inside the bracket, that's nicer. The CT, and what do I have to integrate, what do I have to differentiate in order to get minus cosine? I think I have to differentiate minus sine, right? So this is minus CT sine CT. What about the CT? No, this is wrong. This is wrong here. Let me see. If I differentiate this, I get a C out, right? There's something wrong with the dimensions. This is the length, this is the length, this is dimensionless, fine. This should be dimensionless. This is wrong here. I have a naught half, I integrate. I have to integrate c times a, so I have a c here. Yeah, of course. Yeah, it's correct. I get a 1 over c here. I get a 1 over c here. Now it's correct, right? I have this c here, and if I integrate this, I get a t. Integral over 1 dt gives a t, and integral over this dt gives this expression. Because if I differentiate this, the c goes away. So I think now it's correct. I can write this in a nicer way by pulling the c into the bracket, then I have ct minus sine ct. So that's a parametric form of our curve a as a function of t. So I have the a as a function of capital T. I have c, or let me plot ct, doesn't matter. Ct as a function of capital T. So I get a parametric form, and it's given by this expression here. Have you seen this before? Does anybody know what kind of curve this is? I'm fairly sure everybody has seen this in some elementary course, could be a mechanics course or something like that. It's a famous curve. So yeah, it's a pity that elementary geometry is no longer taught in an intensive manner. So for former generations, this was a much more important subject. That's a cycloid. That's a cycloid. So that's how it looks like. So it starts at 0, and here what ct is. This is the little t. So the little t should be. Let me see. If the capital T is c times t, quite nonsense. If this expression is 2 pi, what is the little t doing? The sine of 2 pi is 0, so this is c 2 pi c pi a naught. Yeah, I think that's it. The 2 goes away, c pi a naught. And that's true. This has dimension length over time. This is, then it's wrong. My goodness. Ct, let me plot t. It's a naught times 2 pi. This is a naught. Here I get a 2 pi divided by c, then it's a over c. I think now it's correct. A over c. A naught over c.
Where's the pi?
It's gone away. Because I have to... No, it's not gone away. Let me see. Sorry, the 2 has gone away. The pi should be there. Yes, the 2 has gone away. Okay, anyway, so the universe begins really with a big bang and it comes back in a big crunch. Yeah? So why it is called cycloid? You know why it's called cycloid? So if you consider a wheel which is rolling, and you fix a point on the axis, then this point on the axis during the rolling process runs along this curve. Yeah? So this is a famous parameter representation of the cycloid. And if you want to solve it, if you want to eliminate the capital T from these two expressions, you cannot do it in the form of elementary functions because it's a transcendental equation. So that's a universe, a dust-filled universe without a cosmological constant and k equal plus 1. So it's a universe with a big bang and with a big crunch. Okay. So let's discuss the other two cases and then combine all three in one picture. So now let's do the case k equals 0. Oops, that's the simplest case. In this case, I wouldn't have to do the detour via the conformal time, but just for consistency, let me also solve this in terms of the conformal time and then make the transformation. So the equation for k equals 0 is, then the first term is gone. It is, the version with a capital T. Where is it? Here, this version. This version with a capital T. Here, this version. So I have, 1 over a squared. Yes, it is solved for the derivative. dA by dt squared is just c squared a naught a. That's it. K is 0. And I think I can solve this. So this gives dA divided by root a is c root a naught dt with a plus or with a minus, right? And what do I have to differentiate in order to get 1 over the root? I have to differentiate the root itself, right? With a factor 2. Yeah? If I differentiate this, I get 1 over the root. And on the right-hand side, I have plus minus c root a naught. Yeah, again t minus ti, but again I choose ti equal to 0, so that I have at capital T equals 0, I have my scale factor equal to 0. So the Big Bang is again at t equals 0. So this means that a of capital T is this thing squared, gives c squared a naught t squared over 4. Okay, that's it. So this is in the conformal time, the universe, the scale factor of the universe expands like capital T squared. Yeah, so it's a parabola in this diagram. But again, we are more interested in the representation of A as a function of little t. So what's the transformation? The transformation is, so t is integral A d capital T. So this is A is this here. Integral c squared a naught over 4 t squared to capital T. So this is c squared a naught over 4 t cubed over 3. Again with a constant, with an integration constant which I set equal to 0. So little t equals 0 corresponds to capital T equals 0. And now I can express a scale factor in terms of, in terms of the little t. I have it here in terms of the capital T. It is c squared a naught over 4 t squared. And for t squared, I can now introduce this expression. So I get c squared a naught over 4. And now something with the power, it is squared. And here I have to take the cubic root. So I get this, and all this comes to the other side, right? So this is 3 times 4 divided by c squared a naught. So you see it's a bunch of constants, and then it's the t, of course, the t, that's the main thing. So it's a bunch of constants, which I combine into a new constant b times t to the power 2/3. And maybe you remember that we have considered this spacetime already. Yeah, so the metric is now, let me write down the metric, c dt squared. It's a scale factor squared, so this is, plus here. B squared t to the power 4 over 3. And this is a universe with k equals 0, so I have here d chi squared plus chi squared, the omega squared. Yeah, the eta is just the chi. So that's the universe, and this is the Einstein-de Sitter universe. Yeah, this is the universe. Just a second. The universe where the debate between Einstein and de Sitter then came to an agreement. So this is called the Einstein-de Sitter universe, and we can plot the scale factor. Oops, that was not a good idea. Einstein-de Sitter universe. And this, I have already plotted the scale. No, I have not plotted the scale factor. T A, it is, what is it? T to the power 2 over 3. Yeah, it's something like that, right? So it goes up forever. So that's the scale factor. There was a question?
Yeah, in the metric, shouldn't it have to be t over 2? T to the 2 over 3? Instead of 4 over 3?
This is a scale factor squared, which I have to write here, yeah?
Okay.
In this place I have the scale factor squared, so it's b squared and also this expression squared, so I think it's correct.
But there's still c missing.
I'm sorry?
Minus c squared dt squared.
C squared, yes, of course, thank you, yes. Okay, let me see if I get my notes back. So the Einstein-de Sitter universe is a dust-filled universe with spatially flat sections, and it's expanding forever. And for many years, this was actually the favorite model in cosmology. So most people thought that this is a reasonable model for our universe, at least now. Maybe not in the early times, But I think as a model for the present time, it was taken seriously, and actually people thought that it would be true up to the late 90s. Yeah? So up to the late 90s, one thought that this part of the graph would be a good model for our universe if we are here, say, or something like that. It's maybe not, or probably not, a good model in this area. Yeah, so in the 1990s, people knew already about inflation, that there certainly was a period where the universe rapidly expanded. And of course, dust is not a good model for the very early universe, one knew this for sure. But for the present universe, one thought it's a good model. And this model gives, you see, it's decelerating. Yeah, it's decelerating. It's expanding, but the expansion becomes slower and slower. It's decelerating. Actually, we calculated the deceleration factor for this space-time, and it came out to be 1/2. Yeah, the Q is 1/2. And for this reason, many people favorize this value of Q equal 1/2 for our universe. Then the supernovae 1A observations came about, and they demonstrated that the Q is actually negative. So this model is now out. Yeah? It's no longer a good model for our present universe, because we have good evidence that there's a negative deceleration parameter. And the usually accepted explanation is that there is this dust, all right, yeah, and it is there, and it gives a certain contribution, but there's also something else which plays an important role. That's what we call dark energy, and this dark energy makes the Q negative. Yeah? So we have a combination of various components, and in the early universe also other components play an important role. So for this reason, the Einstein-de Sitter universe is certainly not the whole truth of the story, but nonetheless, it's part of what we believe that it is a true story. So for this reason, it is still to be taken seriously. So, and then let's do the one k equal +1, the last thing which is still open. So then I have to solve this differential equation again. Oops.
Did we start with k equals +1?
Yeah, at least that's what we wrote.
I'm sorry? Oh, -1 is missing. -1 is missing. Yes, we have done already the cycloid, and now we get, we do the third case. So now I have to solve this differential equation here with k equal -1. So then the differential equation is dA by dt squared. Here I have it written with, oops, in the form I want to use it, is c squared, oops, and in the bracket I have a naught a plus a squared. Yeah, there was minus k times a squared, and the -1 times minus now becomes a plus. So the differential equation is dA over root a naught a plus a squared is plus or minus c dt. So it's the same type of integral we had for the case k +1, but now with a positive sign in front of the leading order term. And this makes a difference between sine and hyperbolic sine if you solve the equation. So the solution to this equation, let me again just copy it from my notes. K equal -1 is here. Yes. So the solution is, this is, in the other case we had the inverse cosine, and here we have the inverse hyperbolic cosine. And this is because I have the other sign under the square root, but this time I hope I got it correct. It's 1 plus 2a over a naught. And of course this is ct minus a constant, and we will see how to choose this constant in a minute. So then I get, if I solve this for a, I get a is a naught half, and this comes to the other side. So it's ct, and I think ti is again 0. Ct minus the hyperbolic cosine of ct. Let me see if I have again a equals 0 and capital T equals 0. So if capital T is 0, this is 0, and the no, it's nonsense. What did I do here? See, yeah, this is true. 1 plus. Oh, good. I should get a -1 here. And this is only in the argument. Here is this 1. This is 1. And the sign is wrong, right? Let me see. So I solve for A. Then I have on the other side the cosh. Yeah, that looks better. The cosh. And this comes to the other side, so it becomes a -1. That's it. And now you see if capital T is equal to 0, the cosh of 0 is 1. 1 minus 1 is 0. So I have indeed the Big Bang at T equals 0. So this is, it has the same form as for the cycloid, and also the T has the analog form, but now with instead of trigonometric functions, we have now hyperbolic functions. So if I want to determine the C, T is A O A T. So what is this? If I integrate this over T, I get the A naught half. If I integrate the cosh, I get 1 over C the sinh. And if I integrate the -1, I get just the T. So if I multiply this out with the C, I have sinh CT minus CT, yes. And this is again a parametric form for a curve which cannot be written explicitly in terms of elementary functions. Yeah, it has the same form mathematically as a cycloid, just with the trig functions replaced by the hyperbolic function. So you might call it, and I think it is sometimes called in the literature, the hyperbolic cycloid. The ordinary cycloid is a circle rolling on a plane. The hyperbolic cycloid is a hyperbola rolling in quotation marks on a plane. Can you imagine this? So, and then one point comes up, and actually it expands. It goes up forever. So the graph of the function is. Yeah, I didn't write the argument because I represented it in parametric form, right? So it just goes up forever. It just goes up forever. So we can combine the three cases now in one picture, and it's a famous picture which you find in every book on cosmology. So the summary of these results is that you can plot all three cases in one diagram. Scale factor as a function of t. So we had the cycloid for k equal +1. So it's a spherical universe which expands and then undergoes a big crunch. We have for k equal -1 this here, which goes up forever. And as a borderline case, in case k equals 0, the Einstein de Sitter universe, which expands and just makes it to infinity. And this is exactly the behavior which we have already written from this analogy with mechanics, right? Oops. Where's the picture? Yeah. So that's the cycloid. It starts at 0, reaches a maximum, goes back to 0. That's the ever expanding case k equal -1, and that's the ever expanding case k equals 0, the borderline case. Okay, so what or who decides if our real universe expands, or, well, first of all, I should emphasize all three of them are decelerating, right? We have no cosmological constant, so the influence of the self-gravitating dust, the self-gravitating effect of the dust will make the expansion slowing down, yeah? Because under their own gravity, the particles want to contract. So all of them are decelerating, and all of them are non-static, yeah? So we have done the static case separately, because this method by which we solved the equations didn't work for the static case. So the static case is not included in the picture. So what remains if we include the static case are just these three cases. And the question is who decides in which universe we are in? Well, the usual way astronomers label this is, and actually this is, how should I say, determined by observation. So the observer lives now, and he can do observations now. So what can he determine from observations? He can determine, for instance, the Hubble constant now, the deceleration parameter now, and so on. So what astronomers want to do is, they want to characterize the behavior in terms of these parameters. So let's ask a question. Let's assume we are here at some certain time t0, and then we have the scale factor here, the scale factor here, or the scale factor here. We also have the derivative of the scale factor in these 3 points, so we can calculate the Hubble constant in these 3 points. And the question is, how is the Hubble constant in these points related to the mass density? And obviously this value of the mass density in relation to the Hubble parameter determines if the universe will expand forever or if it will recollapse. So this is also intuitively clear. If the mass density is bigger than a certain critical value, then the thing would recollapse. Then the initial push, the initial explosion which pushed the particle outwards was not strong enough in order to prevent the thing to fall back. If the mass density is very big. If it is not so big, then actually the initial push will be big enough to make the particle expand forever. And this relation, this determination of a so-called critical density, this is crucial for the way in which solutions are parameterized nowadays by cosmologists. So let me do this for the dust, but I think I have to clean the board for this. So this will introduce these famous parameters, this density parameter omega, which you have certainly seen in the literature before. So we will now determine the omega for dust solutions. What should I leave on the board? The differential equation. The differential equation. This is this here. Yes, I should leave this. Or rather the one with a A0. Yes, this here. F1 double prime. I need this. Oops. Actually, I should say that some people reserve the word Friedmann solutions to these dust solutions, because these were the solutions which he really discussed in detail in his paper. But it has become common to use the word Friedmann solutions in a more general sense. Actually, which perfect fluid solutions we call dust solutions, people wouldn't agree. So one certainly wouldn't call any Robertson-Walker spacetime a Friedmann solution, although it is a solution with a perfect fluid with some pressure and some density. But many of them are unphysical, and one wouldn't say that this is a Friedmann solution. So I would certainly call the dust solutions Friedmann solutions, and also the radiation solutions, which we do next. And but not all of them. So which one would call Friedmann solution is a matter of taste. Okay. So let me write this equation F1 double prime again. So, I forgot something. I said in the beginning that when we have solved the differential equation with an A0, then we determine the mu in terms of the solution by this equation here. By this equation. Yeah? So for each of the 3 cases, you can determine the mass density from this equation. Yeah? And you see, of course, if A is 0, the mass density is infinite. Yeah? So what you consider here, when here the A is 0 at the beginning, and it is 0 for all 3 solutions, this is really a big bang in the sense that, and it's a singularity in the sense that the mass density is infinite. Yeah? It's an infinite density initial singularity. And it's also a curvature singularity, because the mass density via Einstein's field equation is related to certain curvature quantities. So you can calculate that it is indeed also a curvature singularity. Okay, so in the case of the cycloid, the recollapsing universe, with a mass density which is infinite at the beginning, then it becomes smaller, and then it becomes infinite again. In the other two cases, it begins with an infinite value, and then it becomes smaller, 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 obviously. Yeah? So the mass is distributed over bigger and bigger volume. And now let's see how the mass density at one particular instant, let's say now, instant t0, how the mass density is related to the Hubble constant of the universe. That's what I want to find out. So let me write the equation again. So the equation was Ka plus A prime squared. Oh, let me, yes, I think I solved it for what? No, I leave it in this way. I leave the mu on the other side. I think that's a good idea. So I have K times A plus A prime squared A over C squared. A over C squared. We are considering the case lambda equals 0, so there's no lambda term, and on the right hand side I have kappa over 3. Kappa over 3 C squared A cubed. Yes, I have the A cubed here. A cubed mu. Actually I want to solve for mu, so let's divide everything by A cubed. I have solved it for the mu, and now I want to see if I can identify on the right hand side somewhere the Hubble constant. Yes, here I can identify the Hubble constant, so I can write this in the following way. It's K over A naught squared, A squared. I'm jumping ahead. K over A squared, and here I have A over A cubed. So this is A prime over A squared. And this is a Hubble constant if I evaluate this at a time t0. And 1 over C squared. Yeah, okay, let me write it this way. Kappa over 3 C squared mu. Yes. So if I multiply with 3 over C squared, 3 over C squared K A, and evaluate at t0, at the time t0. Then I have this here. Then this here, A prime over A, is a Hubble constant. Yeah? So this is h of t0 squared. That was the way in which the Hubble constant was defined. And I've multiplied by this, so I get it with a 3. Is that true? I think I also divide by kappa. And then I get, on the right hand side, only the mu at the present time. And now you see that if we assume that this is the correct model of our universe, so one of these three cases are really satisfied in our world. Let's assume this for the sake of argument. Then we can decide which of the three cases it is. K equals 0, K equals minus 1, or K equals plus 1, just by comparing the mass density now with the Hubble constant now. Yeah? So when we see if the mass density is the dimension correct? Let me check. It looks a bit strange to me. Mu is 3k over kappa c squared a squared. That's correct. And this is 3 over kappa. I have a c to the 4 here. Yes, of course, I get a c to the 4 here. I multiply with this. Yes, now this looks more reasonable. So let's call this quantity, it must also has the dimension of a mass density, right? So let's call this mu critical at the time TO. Yeah, it also depends on TO, of course. And then you see, if the true density now is bigger than the critical density, which is associated with this value, then we have k equal plus 1, right? Then k must be positive, so k must be equal to plus 1. If the true density now is equal to the critical density, then we are in the case k equals 0. And if it is smaller, then we are in the case k equals -1. So you can decide which of the three cases we are in. If we have measured the Hubble constant, actually we have done this in our universe now with a fairly good accuracy, and if you have some estimates about the mass density now, this will decide in which of the three cases you are in. And what you introduce in cosmology in order to characterize these three cases is a quotient of these two quantities. So then the question is it bigger than 1 or smaller than 1? And this is called the density parameter. The density parameter. What we are doing here is a density parameter for dust. Yeah? We will also do it for other matter contents later. And the density parameter is unanimously called capital omega in the literature. And dust, what we call dust, what we have solved here with the field equation for dust, is what astronomers or cosmologists call ordinary matter. Yeah? So they usually use an index little m, which reminds you of matter. So that's the galaxies. Yeah, the galaxies can be modeled fairly well in terms of a dust. So this is the contribution to the total mass in the universe, or total energy in the universe, which comes from the galaxy. This is characterized by this omega m, which of course also is a function of time. So we evaluate it at our present time, and this is just mu TO over mu critical TO. And you see, it is it's not made quite analogous, so it's not positive, 0, or negative in the three cases. It is bigger than 1, equal to 1, or smaller than 1 in the three cases. Yeah? And this density parameter will accompany us for a while. So how much time do I have? I have about 10 minutes. I think this doesn't make sense to begin with the cases with lambda. I will discuss the cases with lambda not in full detail, only I will tell you what a lambda does. Actually, you might guess this already, what a lambda does with the three cases. So we have the three cases, recollapsing, expanding forever, and the boundary case, the borderline case. And, a positive cosmological constant will try to push everything apart, and the negative cosmological constant will make everything contract stronger. And then we have to see how to balance these things out. Maybe it's more useful to spend a few minutes for comparing again the three important models which we have learned about now. So we had Einstein's static universe. So three cosmological models which you should keep in mind, which you should know, right? So Einstein's static universe. We had the de Sitter universe. And we have the Einstein de Sitter universe. These are the three things you should have heard about and you should remember from a course on cosmology. How are they characterized? So here we have lambda bigger than 0, we have k equal +1, and we have mu bigger than 0 and no pressure. Yeah, for all three we have no pressure, but for completeness let me also write this. So this is a universe which is static. So this is a solution also with positive cosmological constant, also with spherical geometry, but no mass density. It's a vacuum solution. And is it static or is it not static? Well, if you look at the standard representation, which we still have on the board, here's this picture. So if we consider the slicing into these spheres, then of course it's not static. Yeah, it is collapsing and then re-expanding. We have already considered two different slicings of the De Sitter universe. You can slice it into flat spaces, spaces of constant curvature 0. this covers only half of the hyperboloid. And you can also slice it into hyperbolic slices. This covers only the future cone of a particular event. And so in this sense, this is a natural slicing. And in all three slicings, we have a time-dependent scale factor. But this does not mean that the de Sitter universe is not static. Actually, you can introduce a fourth slicing, which is not a slicing into constant curvature spaces, but a fourth slicing where the t-lines, the lines perpendicular to the slices, are actually integral curves of a Killing vector field. So the observer moving on these t-lines perpendicular to the fourth slicing, they always see the same universe. So the space-time is static for them. And we will discuss the static slicing, which is not a Robertson-Walker slicing. Yeah? It's not a slicing into constant curvature spaces. We will discuss the slices in the worksheet on this Friday. So the de Sitter universe has many phases. So I don't write here non-static because you can find a slicing that it is static, at least for part of it. Actually, those of you who are familiar with the Kotler space-time, which is also called the Einstein-de Sitter space-time, they know this slicing. It is just the Kotler space-time and the standard representation where you set the mass equal to 0. Yeah? Then you get the de Sitter space-time. Why is the Kotler space-time also called the Schwarzschild-de Sitter space-time? Because it has two parameters, m and lambda. If you set m equal to 0, you get the de Sitter space-time. If you set lambda equal to 0, you get Schwarzschild. Yeah? So it's not named after Schwarzschild and de Sitter because they invented this space-time. They did not. But it's named after them because you get these space-times as special cases. And this slicing, which we will do in the worksheet on this Friday, is just the static slicing of the Kotler space-time with mass equals 0, which is de Sitter. Okay, and then the third case, that's what we have done right now. So this is no cosmological constant. It has k equals 0. It is spatially flat. So the natural topology is that of an infinite 3 space. It has a mass, and it has no pressure. So these are the three universes which you should have heard about, and which you should not confuse, right? It's easy to confuse them because the names are occurring in different combinations. So, okay, actually I think it doesn't make sense to begin with a discussion of the lambda. Are there any questions? Yeah?
Can you take this equation that you call F1 double prime there? Then you say the right-hand side is some conserved total energy of the universe. Mm-hmm. And can you integrate all the three terms on the left-hand side as, let's say, contribution from curvature, contribution from initial conditions that you cannot get rid of, and a contribution from cosmological constants?
Yes. So I'm not sure if this could be heard over the microphone. The remark was that we interpret this as a conserved mass, or more generally speaking, if we consider more general cases than just the dust, then we would have a conserved energy here. And the remark was that the three terms on the left-hand side could be interpreted as three different contributions to this total energy. So one comes from the curvature, one comes from the behavior of the scale parameter, which is at least partly determined by the Hubble parameter, and the third one comes from the cosmological constant. And that's exactly the way in which this equation, or maybe even the generalized equation where we also have a pressure, is interpreted if we introduce these density parameters. So here we have introduced the density parameter for the mass. One can also introduce density parameters for the other contributions, and we will do this. And then we have an interpretation of this total conservation law as being composed of contributions from different terms, each of which can be interpreted quite nicely. Yes. So this was a perfectly true remark, and we will come to this. Yes. Any more questions? If not, I think we stop here and see you again on Friday.